Good morning, everyone, and welcome to another exciting session of Digital Vidya webinar. The topic for today's webinar is Introduction to Deep Learning and Neural Networks. And to lead the webinar, we have with us Chandi Mahanta, who is a senior data scientist at MathLogic and also the co-founder of Deep Learning Track. Janvi has 13 plus years of expertise in data analytics and strategy, along with the knowledge of neural networks, deep learning, text classification, with a focus on NLP and working knowledge of Python programming. I welcome you, Janvi, in this webinar session. And now over to you.
Okay, thanks Niharika for the introduction, and thank you all for joining me in today's session. Okay, so deep learning today is a very is a field which has a lot of prominence, and it is gaining a lot of importance and relevance with applications in many various fields, right? And you all being data science practitioners or data science aspirants, you all eventually will have to get into deep learning because that's the future, right? However, today I feel there is a lot of hype around it. So, what I want to do in today's session is really give you a very basic, simple, conceptual understanding of what deep learning is, how is it different from traditional machine learning, and then go into a little bit of a deep dive into neural networks because that really forms the foundation of deep learning. Okay, so let's get started. Okay, but before we get into all of that, I would like to walk you through a few tasks where machine learning and deep learning have been able to achieve a lot of success to a large extent. Okay, so let's take the game of chess. So, if you recall, many of you would recall that in 1980s, IBM Deep Blue Computer actually defeated the reigning chess grandmaster Garry Kasparov in a game of chess, right? It created some controversies, but it was really a milestone for artificial intelligence. Why? Because chess as a game is not simple. It's a very complex game. It requires a lot of strategic moves and a lot of forward thinking moves, right? So the question is, how did a game of chess or how did a computer program actually defeat a chess grandmaster, right? Now, a game of chess, although it's complex, but it is still a well-defined game. It has all the information required to win. So it has defined rules, moves, as well as modes. So if we train a computer program enough, it has all the information and it has all the capacity to win the game of chess. Okay? But if you really think about it, winning a game of chess is still the first step for artificial intelligence. Now you might ask why, right? Because in real life situations, for example, if we take the next task in hand, which is predicting house price in a locality, you know, all the information that is required to predict house price may not be known, right? For example, we may know some of the information, like we know that house size can have a bearing on the house price, right? The place where or the location of the locality may have an impact on the house price, but all the information may not be known or even quantified, right? But today what we have been able to create machine learning algorithms that have been able to handle these real life complex problems successfully. Question is how, right? Now, the way these algorithms, these machine learning and even deep learning algorithms are defined, primarily machine learning algorithms are defined. Firstly, what we do is we put together a set of factors or features that impact the task at hand. For example, in this case, house size or house location, where it impacts the task at hand, that is predicting house price. And then we define a mathematical or a statistic model and then train it on huge amounts of data. Okay, so now you can see that when you compare this task of predicting house price to winning a game of chess, it is a real advancement in artificial intelligence, because here we are applying machine learning algorithms to solve problems where all the information is not known. There is some amount of uncertainty. Okay, so moving on, so far so good. But today, what we are trying to do, we are trying to solve even more complex problems. Okay, so let's take these two examples here. The first one is driving a car. So, why is it so hard for a machine to learn successfully driving a car? Why can't we define a machine learning algorithm and define all the features just like we did for housing price prediction? But if you think about it really carefully, driving a car can be very, very difficult. And I don't think there is any human or anybody out there who can define all the features or factors that are required to drive a car successfully, right? So we can define some of the factors. For example, if there is a car coming from the front, we can say that, stop the car. Or when the traffic light becomes red, we can say that stop the car, right? We cannot define all the features because the features are innumerable, and all the features are important because our error rate has to be like almost zero, right? Similarly, if you take the task of recognizing an image of a dog, right? Again, we cannot define all the features that are required for this task. You may say that if an image has a black circle, it could be the nose of a dog. But then again, you can have many animals, even cats may have black noses, right? So it's incredibly difficult. So this is where deep learning comes into the picture. Deep learning algorithms, what they do is they are really trying to solve these incredible complex problems by learning these features on their own from the data. We don't have to define the features the way we did in house price prediction, right? So essentially, deep learning, it is a branch of machine learning itself. The difference here is that it tries to learn these features on its own from huge amount of data that it is getting trained on. And this is the basic difference between a deep learning and a machine learning algorithm. Okay, and now you can see that why deep learning is the next level of artificial intelligence, because it is helping us to solve incredibly complex problems which we were not able to do so earlier. Okay, so moving on, this is what we talked about so far. The key difference between a traditional machine learning and a deep learning is, in traditional machine learning, like the task of predicting house prices in locality, we define the features and then the algorithm uses those features, get trained on huge amounts of data, and then does the prediction. However, in deep learning, the algorithm is learning the features on its own from the data, then does the prediction. And this learning the features on its own is a process called representation learning. And through that, deep learning is able to solve many complex problems in natural language processing or in image recognition. Okay, and this is an important slide because it talks about a typical structure of a deep learning network. Okay, so what we have here is we start off with the input layer, which is in this case are a set of images of handwritten digits and alphabets O and A and 0. The deep learning algorithm, what it does is that it takes these input images and creates its own features from these images. So the features that it creates are H1, H2, H3, which we call the first level of abstraction. It then creates a second set of features, H11, H12, H13, from these features H1, H2, H3, which So you can see that higher the layers, the more the algorithm is learning from the data. Okay, and the better it will be in its task or its understanding. So this is essentially how, at a very broad level, how deep learning learns and does prediction, and why it is able to do a lot of complex tasks in image recognition and NLP. Okay, moving on. This is a summary of what we have learned so far. So deep learning is a branch of machine learning. The difference between traditional machine learning and deep learning is learning the features on its own from the data and does a prediction, whereas in traditional machine learning algorithms, we are providing the features, and this is the reason it is able to do very complex tasks, and therefore today has applications in many fields like business, medical, agriculture, and even defense and government. You might have heard about it. And you might also observe here that because it is solving these complex problems, it needs a lot of data to get trained on, right? And that is the reason that today we have, it requires a lot of processing power, right? But today we have the infrastructure in terms of GPUs and TPUs which can handle that kind of processing power, and that is another reason why deep learning is very, very successful these days. Okay, so moving on. So what have we done so far? What we have understood so far? What we have understood is a very conceptual level understanding of what deep learning is, how is it different from machine learning, and its relevance. Okay. Now, to further understand deep learning, it is important to understand neural networks, which really forms the foundation of deep learning. And for that, I would like to take you through the evolution of deep learning, because through this evolution, I can explain or give you an understanding of the inner workings of neural network, which really is, as I said, the foundation of it. Okay. So where did it all start? It started around early 1940s when scientists started techniques in terms of the cells, the brain cells called neurons, processes those inputs into sound and right? Think about it. If you put your hand on a hot pan, say, so these signals will go to your neurons, brain cells. The brain cells will process it and gives out an output, and basis that output you actually react, take out your hand from the pan. So scientists started. Hello, am I audible? Okay. Niharika, is it better now? Please stop me if required whenever you feel that it is happening again. Okay, so where was I? Okay, I was talking about the neuron, right? So this is how your brain actually works. So brain also, so scientists wanted to understand how your brain cells or neuron work. So they tried to replicate it using a small, by creating a small prototype of a neuron, right? Which actually led to the development of perceptron around 1940s, which I'm going to talk about in the next few slides. And perceptron was actually the basis of neural networks, right? However, the perceptron or the neuron that scientists created was a very, very simple model, and it didn't have too much of a real life applicability. So it was critiqued quite a bit, and specifically around 1960s or late 1960s, a paper was written by Minsky which critiqued the perceptron, and people lost faith in artificial intelligence and neural. And that phase was called the AI victory. But around 1980s, again renewed interest started, and with probabilistic theory and nonlinearity and optimization. And then in 2006, George Hinton, many of you would have heard about him, considered to be the father of deep learning, wrote a paper on deep belief networks. And from then onwards, the research on deep learning frameworks. Okay, so this is a brief overview of the evolution. Let's go into the perceptron, which will help us understand neural networks. Okay, so perceptron. Now, perceptron was given by a scientist called Frank Rosenblatt. Um, Niharika, can you still hear noise in the background? Okay, is it better now? Can you say yes again? Then I'm sure. Okay, I assume it's yes, and sorry for the noise. So, okay, so what I was saying is about, okay, is it better now? Okay, great. So, so the concept of perceptron was given by the scientist called Frank Rosenfeld, and it was again based on the idea of neuron by McCullough and Pitt. So let me explain this through an example. Let's say you are asked that can you predict if Donald Trump is going to win the next election? Many of you would know that he is up for re-election next year in 2020. So if somebody asks, can we predict if Donald Trump is going to win the next election? So what would you do? You will put together a set of factors that is going to impact his re-election, right? So let's say you put together three factors. So first one is perception of his policies. One, if it is good. Zero, if it is bad. Unemployment. One, if it is low, and zero, if it is high. Immigration policy. One, if it is tough, and zero, if it is lenient. Okay, so these are your inputs, x1, x2, x3. But in your mind, you wouldn't rank all of these inputs at the same level of importance, right? So you would attach a level of importance to each of these inputs, x1, x2, x3. And that importance is given by the weights, W1, W2, W3, which is nothing but the importance that you attach to the weights. Okay. So let's say basis this, you have come up with x1 is equal to 1, the first input, and you give a weight to it as 0.7. X2 is 0, weight attached is 0.1, and then x3 is equal to 1, and the weight that you attach to the third input is 0.2. Now, using all of this, now you define a variable called Z, which is nothing but the weighted sum of these inputs. That is, Z is defined as x1 times W1 plus x2 times W2 plus x3 times W3, which really comes out to be 0.9 in this example. Okay. Now, at this stage, you define a threshold value. Okay. Let's say you have thought of a threshold value of 0.5. So now you're putting together a rules. You're saying that if your value of Z is greater than the threshold value, which is 0.5 here, then Y is equal to 1. So the output is equal to 1. That means Donald Trump is likely to win the next election. Okay. However, if your value of Z is less than 0.5, you say that Y will be equal to 0 and Donald Trump is unlikely to win the election next. Okay. So this is, in short, this is how perceptron works. It's a very simple model, and it is a linear model, and this is how it was developed. Okay, but there are many issues with a perceptron. Firstly, you can see from the graph on the right hand side, there is a sharp transition from y is equal to 0 to y is equal to 1, right? So when your value of z is less than 0.5, y is equal to 0. And when your value of z is greater than 0.5, in the earlier example, the y value is equal to 1. So y is actually a step function, here shown on the graph given by the neon lines. Okay. Also, certain values of z, for certain values of z, the output decisioning could be very harsh, right? So if your value of z is 0.51, y is equal to 1. But if your value of z is 0.49, y becomes 0, right? So the decisioning is very harsh and it may not apply to real life situations. Okay. The other problem is that if you change W1, W2, W3 by little amounts, for certain values, y can flip from 0 to 1. So perceptron as a model inherently could be very, very unstable, right? So for these reasons, people then moved from a simple step function that we talked about earlier to what we call a sigmoid function to calculate the value of y. So the question is, what is a sigmoid function? You can see that in equation 1 here, okay, on the slide, where in the sigmoid function, we describe y as a non-linear function of z. Many of you would, who are practicing data science and who have some knowledge of data science, would recall that this is actually the logistic function. And it is given on the right hand side as the neon curve. Okay, the important thing to note here is, if you see here, y is no longer a step function. We saw earlier, right? Y was a step function, but now it is a smooth line. So what are the advantages of moving to a sigmoid? Firstly, smooth transition from y is equal to 0 to y is equal to 1. Secondly, y is no longer binary. We saw earlier that y could take only the values of 0 or 1, right? But now with sigmoid, y is actually a continuous value between 0 and 1, and therefore it can be used as a probability. Okay, so now we have moved from a linear calculation of y as in a perceptron to a non-linear sigmoid calculation of y, as you can see on the left hand side. Okay, now question is, how do we arrive at the neural network structure seen on the right hand side, which we also call as an MLP or multi-layered perceptrons, from this simple model that we talked about using sigmoid? So if you look at the neural network that is given on the right hand side, if you look at it very carefully, it is nothing but a collection of the simple models that we talked about earlier, right? So what we are doing here, we are using inputs x1, x2, x3 and weights w1, w2, w3 to get the output O1 as in the simple model, right? Applying the same process that calculates Z and then applying sigmoid and then get the output of O1. Now, using the same inputs x1, x2, x3, we define another set of weights, that is W4, W5, W6, and we come up with another output O2, right? And then using O1 and O2, we are now calculating the output Y given in orange. Okay, so so what you see on the right hand side is a compilation, or it's a collection of different simple models with different weights. Okay, and this is the basic structure of a neural network, or a multi-layered perceptron. Okay. So now you might ask that what is the advantage from moving from a simple model to this collection of models, as in a neural network, right? So if you think carefully, in the simple model, we had one set of opinions or weights, W1, W2, W3, attached to the inputs, X1, X2, X3, and we got one output, O1. But in the neural network, we brought another set of weights, W4, W5, W6, to get another output, O2. And O1, O2 then predicts the Y. Now, such a model where we have more than one opinions or one set of weights, okay, there is always more learning. Okay, we learned in the simple model, we are only learning using one set of weights, but here we are learning using two set of weights. So definitely such a model is likely to be better because the learning is definitely more, the model is understanding more, right? And that is the advantage of a neural network over the simple model. You might also ask that how neural network can be considered as the foundation of deep learning. So if you compare this neural network to the structure that I showed on slide 5, it is very, very similar, right? So just like this structure where the deep learning model is learning from the inputs its own feature, here also the neural network is learning from the data and creating its own features and then doing the prediction or calculating the value of y. Okay, so here you go. We have created our first very basic structure of a neural network from a very simple non-linear model. Okay, so let's do one thing. Let's now try to create a very simple neural network architecture for image classification. Okay, but before that, many of you would be aware, but for those of you who are not aware, let's understand how an image can be actually quantified. Okay, an image is nothing but a collection of numbers which we call as pixels, and these pixels range from the value of 0 to 255, which really gives its intensity. So if you look carefully, this is image is that of a handwritten 8, and where 8 is written, the pixel values are higher, which really gives its intensity. Okay, so this is what an image is. Now let's say we have a task to classify this image of a handwritten 8 given here. Okay, so what we have to do, in short, we have to calculate y, which gives the probability that the image here is that of a handwritten 8. Okay, so that is our task at hand. Okay, so now this image of 8 has 28 by 28 pixels. So total number of pixels that are given in this image 8 are 784. So for our basic neural network that we are going to construct, okay, we have 784 pixels that will be our input. So our inputs range from x1 to x784. Okay, so now let's look at the architecture of the neural network at the bottom. So in step 1, what are we doing? In step 1, we are creating 3 models with 3 different set of weights. One given in green, one given in orange, and one given in pink. Okay, and using these 3 different set of weights, we are coming up with 3 outputs, O1, O2, O3. Okay, so in step 1, the total number of weights that we have is 784 times 3. Okay, so that's step 1. Now in step 2, we use features O1 and O2 to get the next set of features O21 and O22, and again the number of features in step 2 is 3 times 2, that is number of weights, sorry, is 3 times 2, which is 6. And in step 3, we finally take features O21 and O22 to calculate y, which is y is now a value between 0 and 1, and y is actually gives the probability that the image at hand, the input image, is actually that of a handwritten. Okay, so this is our very basic structure of a neural network for this particular task at hand. Okay, a few call outs. The first layer is called the input layer. The other two layers are called the hidden layers, and the nodes there, we have 5 nodes here, they are called the hidden nodes. Okay. Second point to note is while creating a neural network, you will have to, the creator will have to decide how many hidden layers should be there, how many hidden nodes should be there, how many weights, and you decide that basis the combination which gives you the most accurate calculation of y. Okay. Okay, so we have created our first neural network. Now, let's consider a situation. I'll keep on this slide itself. Now let's consider a situation where after doing all of this, you get a value of y as 0 0.2. So what does 0 0.2 means? 0 to 0.2 means that the probability that this image is a picture of a handwritten 8 is only 20%. Okay, so which is obviously not correct because this picture is actually an image of a handwritten 8. So there's something we need to change in our neural network. Something is not right, right? So what do we change? Can we change the inputs x1 to x84? No, we can't do that because inputs are given, they are fixed. But what we can change are the weights. Because if you really think about it, weights are nothing but your opinion or your assessment of the various inputs, right? So what we do is we keep changing the weights little by little so that we learn from the process and we get better calculation of y. But we don't want to change the weights too much also because then otherwise the model will fluctuate quite a bit. Okay, so this process of changing the weights by small amounts after every iteration so that we arrive at a value of y which is closer to the actual value is called backpropagation. So this process is an optimization process, and this process is called backpropagation. When you read papers on neural network, you will often hear this word backpropagation. In simple terms, this is what it is, right? And on this chart, this is the process of backpropagation or optimization is shown. So where what we do is we first, when we create the neural network, we start off with any random values of w, right? So in this case, the weights are a and b. So we start with any random values of our weights a and b, and then we keep changing our a and b by small amounts, and we keep doing that till the time we reach optimal values of a and b, where your calculated value of y is closest to the actual value of y. So in the example earlier, we get a value of y which is very close to 1, right? Because the image is actually that of a handwritten 8. Okay, so this whole process is called backpropagation, and this is how we optimize our neural network. And there are many optimization algorithms which we can do. Um, the most commonly one used in the industry is called gradient descent. And when you read literature on neural networks, you will hear about gradient descent. So essentially, but in very simple terms, this is what um, an optimization algorithm called gradient descent does. Okay. Okay, so this is how a very basic neural network can be created, and this really wraps up my talk today. And hopefully you have now an idea of a conceptual understanding of what deep learning is all about, and you have now some understanding of the inner workings of neural network. Okay, so Niharika, I have wrapped up my session. I'll be very happy to take any comments or questions at this stage.
Great, Janvi. Thank you so much. It was indeed a valuable session. This is for the attendees. You can now ask your questions, if any. And by the time attendees ask their questions, I'm launching a poll. Kindly put in your relevant choices. I would again like to request to the attendees, if you have any questions, you can ask. Okay, so lastly, I would like to launch another poll for you to share your experience with Digital Vidya's webinars and for today's session. Okay, thank you so much, Janvi, for leading the webinar for us. And it was great having you here. And thank you everyone for being such a wonderful audience.